Hello, my name is Woojin Lee, and today I will talk about our work on VirtualWire, supporting rapid prototyping with instant reconfigurations of wires in breadboarded circuits. This is joint work with Ram Krishna Prasad, Sung-Woo Jae, Yoonji Kim, Ian Oakley, Daniel Ashbrook, and Andrea Bianchi. VirtualWire is a novel tool for prototyping circuits that allows users to insert components on a physical breadboard and to connect them without physically placing wires. Instead, users can design the circuit layout using computer software, such as Fritzing and Autodesk Eagle, to specify virtual wires that describe how components should be connected. With the popularity of electronic prototyping platforms, circuits are now commonly created and built by a broad spectrum of non-technical makers and academic researchers. For such users, assembling circuits by placing wires and components into breadboards remains a challenging and time-consuming activity. The key problems of breadboarding are both simple and fundamental. Components are misplaced, wires are omitted, connected incorrectly, or inadvertently disconnected. Novice and intermediate users have reported that such errors are hard to diagnose and debug. These issues remain an obstacle for exploring breadboarded circuits and contribute to the notion that the activity is intimidating and confusing. Researchers have previously proposed techniques to simplify breadboarding by focusing on qualities such as speed and ease of building the circuit, supporting increased complexity, and the use of novel substrates. A notable work is Circuit Stack, which places circuit topology on swappable conductive sheets clamped under the breadboard. However, making changes to the circuit topology remains laborious, involving redesigning and printing the sheets along with disassembly and reassembly. Other works, such as Vizier, aim to ease the physical construction of circuits, but did not support arbitrary multiple wire connections. You may refer to the paper for more detailed information on related works. VirtualWire's reconfigurability is enabled by a switching matrix, which allows unlimited arbitrary connections on the breadboard, which is instantaneously recognized and reflected in hardware, without needing physical rewiring or disassembly and reassembly. To establish the appropriate size of the breadboard, we extracted metrics related to the size and complexity of circuits of typical Arduino projects in two common maker resources, 15 from the Arduino project book and over 4,000 from the online Fritzing projects repository, which yielded an average of 12 electrical nets. Based on the small size of the circuits in the repositories and in line with prior work, we selected a breadboard with 16 rows, or 16 unique electrical nets. During the use of VirtualWire, as connections are placed or updated on the designated software, the virtual circuit layout is automatically updated on the physical breadboard in real time, producing real electric connections matching the virtual ones, creating a fully functional circuit. The final circuit design can be saved, shared, or automatically prepared for fabrication as a PCB. The prototype breadboard can be detached and immediately used in conjunction with the fabricated circuit. VirtualWire can be used in a myriad of different ways. The basic process of creating new circuits with both analog and digital components are enhanced through the use of VirtualWire. Here's the circuit that controls a microserver motor using a potentiometer and external power source. Also, a sound level visualizer circuit that uses a dual operational amplifier and low-pass filter. These examples were taken from the Arduino Starter Kits projects book and an online maker community's repository respectively, and emphasizes the involvement of processes such as reading analog data, hardware filtering, and PWM output. The user can also easily explore alternative hardware configurations. An example of this would be the reconfiguration of logic gates as shown here using a NAND gate chip. A more practical example would be the use of digital modules that support complementary features such as different communication buses. VirtualWire also supports rapid and seamless adjustments, allowing for the potential to optimize specialized subtasks, such as picking component values among a set of alternatives. For example, we show a case where a low-pass filter is tuned by adjusting the values of the resistors and capacitors in its RC network. VirtualWire integrates with existing design and fabrication tools. For example, it can also serve as an ISP chip programmer tool. Shown here is the VirtualWire's internal Arduino setup as an in-system programmer for the Tiny 85 microcontroller. We conducted 2 separate studies to evaluate the efficiency and experience of using VirtualWire as a prototyping tool. The first study was a performance-based quantitative study. It compared objective measures of performance between VirtualWire and traditional breadboarding conditions by tasking the participants with the assembly of 4 different circuits of varying complexity with each of the 2 conditions. Participants could submit their circuits multiple times until it was submitted correctly, and errors were logged and organized as either self-detected errors or at-check errors, and whether it involved missing or misplaced wires, end components, or inverted components. The second study was an interview-based qualitative study. After a brief demonstration of VirtualWire and a warm-up session with the system, participants were asked to build 3 circuits of various complexity. They then compared these sessions with their prior experience in building circuits. VirtualWire led to statistically significant reduced task completion times. No significant difference was observed between the mean of checks requested in the VirtualWire condition and the mean of checks requested in the breadboard condition. Statistical analysis of error counts showed that VirtualWire also led to significantly fewer errors. We have plotted the duration of each trial and highlighted the times where self-detected errors and at-check errors occurred. The shorter task times and reduced number of at-check errors in the VirtualWire conditions are immediately evident. The statistical analysis along with the visualization supports the claim that VirtualWire can improve not only the speed with which novice users can produce breadboard circuits, but also the accuracy and correctness of their work. It is especially worth noting the VirtualWire reduced the number of at-check errors. We suggest this type of error in particular is challenging for a user to detect and debug during real-life circuit creation, where it is hard to know when errors were committed, which components they involve, and even whether it originated in software or in hardware. All participants praised the system's ability to reduce the clutter and fragility of physical breadboards. Most participants noted that VirtualWire integrates well with normal prototyping workflows rather than disrupt or change practices. Participants speculated on several possible applications for VirtualWire, including educational training, testing components and sensors, and exploring different variations of a circuit. Please refer to the paper for more information on the results of both studies. Some points of discussion before wrapping up. The results of the study revealed possible integrations of VirtualWire within more layered environments beyond circuit prototyping and designing. One such application being an educational setting where the onboard Wi-Fi microchip can be used to publish wire instantiations to all personal devices across a classroom. The use of cross-point array chips to implement the reconfigurability makes its integration with previous related works, such as Virtual Component, which similarly uses cross-point array chips, easier. Alternative modes of implementation may also be explored, such as with FPGAs, which are programmable logic block hardwares. However, if FPGAs only work with digital signals and require expertise in combinatorial logic and are not beginner-friendly. The final direction of exploration would be the use of added assistive interactions. As it stands, VirtualWire does not indicate the correctness of the circuit topology or detect the correct placement of components. That's all for this presentation, and thank you for listening.